Yeah. In our previous sessions, in our previous lectures, we have discussed different aspects of fully miscible liquids. That is, liquids which form homogeneous solutions. In fact, there was a small bit remaining, liver rule, which I did not cover during my live sessions. However, I still have sent you the uh, PPT, PDF of the PPT of about 3 to 4 slides that cover liver rule. So please see that PDF and understand. If you still don't understand, you can always get back to me. I will explain you in detail if you have not understood. Okay, fine. Now we are going to start our discussion on partially miscible liquids. Fine. What do you mean by partially miscible liquids? Now you take any two liquids or a solute and solvent. When you are making a solution, most of the times they are miscible with each other. Only then you are going to make a solution, right? So take sodium chloride, add to water, it's fully soluble. Take glucose, water, fully soluble. And then you take ethanol, water, soluble. You take chloroform, ethanol, soluble. So you take two liquid combinations. The combination is soluble. But there are liquid systems where they are not fully soluble. So if they are not fully soluble, shall we call it that they are insoluble in each other or simply immiscible in each other? We can call like that. But there are some aspects of these liquid system which stop us from calling them immiscible liquids. What are these aspects? The first aspect is we will understand these aspects taking one common example of partially miscible liquid system, that is phenol water system. Let us conduct solubility tests, few solubility tests. Take water and add a small amount of phenol to it. Shake and look at the solubility. You find the solution has become homogeneous. That means water plus a small amount of phenol are soluble in each other. You take now water plus a large amount of phenol, shake, and then look at the solubility. You find that it has not given you a homogeneous solution. Instead, it has given you a heterogeneous solution. Now, how can you distinguish miscibility and immiscibility by visual sensation? How can you distinguish? Whenever there is full solubility, full miscibility, the solution is clear. Solution has single layer. It is clear. It is homogeneous. But if it is insoluble, if the liquids are insoluble, for example, oil and water, how do you say it is the oil is not mixing with water? Why? How? That is by looking at the formation of two different layers, right? Oil will be floating on the top, water is down. And sometimes a turbidity appears. And sometimes droplets form. So whether there are two layers after shaking, or there is turbidity, or there is presence of droplets, oil droplets or droplets of some organic solvents, then we call it is immiscible. So you take water and small amount of phenol, shake well, you find a clear single layer solution. That means it is soluble. The same thing, water plus large amount of phenol, you get two layers. So whenever you get two distinct layers, what is your conclusion? It is immiscible. And then you can also do this in a reverse way. What? You take phenol, large amount, and add few drops of water, small amount of water, shake well. See, it is homogeneous, it is soluble. And then to this same phenol, you add large amount of water, shake, turbidity comes. Okay, heterogeneity comes. So what does it mean? Water and phenol are miscible with each other only when one of the solvents, either water or phenol, is present in small amount. When water and phenols are present in appreciable amount or are present in relatively equal proportions, then they are not soluble. Fine. Then why do we call them partially soluble with each other? First condition is this lower quantity, higher quantity. Second condition is even if they are forming two layers, you take the layer of phenol and you test, there will be water in it. And you take the layer of water, test for phenol, there will be phenol in it. That means they are miscible with each other to some extent. Beyond that extent, they are not soluble. Fine. But what is the scenario in completely immiscible liquids? For example, water and oil. You take water and analyze for oil. Not a trace of oil will be found in water. You take oil and analyze for water. Not a trace of water will be found in oil. That means they are totally independent immiscible systems. But here it is not like that. It is somewhere in between fully miscible and fully immiscible. It is almost in between. To some extent, it is miscible. So, in fact, the layers of phenol and water they are formed. They are saturated solutions of each other. What do we mean by the saturated solutions of each other? That means in the phenol layer, there will be maximum extent of water. In the water layer, there will be maximum extent of phenol. So you can separate the layers and then see it is a saturated layer phenol in water. It is saturated water in phenol. What do you mean by this saturation? In terms of miscibility and solutions, what do you mean by saturation? Saturation means it is the point after which if you add the solute doesn't dissolve. It simply precipitate out. Example, can you make saturated solution of sodium chloride? You can, is it not? You can take table salt, the rock salt in your kitchen, take water, go on adding sodium chloride, solubilizes slowly. And then when you add a large amount of sodium chloride, go on, still continue adding, there will be one point where sodium chloride becomes saturated. And even that extra sodium chloride you add will not go into water. Rather, it separates out from water and collects on the walls of the container. That is what the saturated solution of sodium chloride is. Therefore, you take water, which is now saturated with phenol. You add small amount of phenol. That phenol is not going to be miscible in water because already phenol has got saturated. Therefore, in partially miscible liquids, although there is immiscibility after increasing the amount, relative amount, but the solutions are getting saturated with the other solvent. Okay, fine. So now we call that the two layers are in equilibrium. And these layers are called, each solution is called conjugate solution of the other. Do you understand? So water is a conjugate solution of phenol. Phenol is a conjugate solution of water when during equilibrium. Okay, fine. Now, we have to understand one more thing. What is making miscibility? What is causing miscibility and immiscibility? It's the relative amounts. When one of the solvents is present in small amount, the solution becomes miscible. When the concentrations of both increase relatively, the solution becomes immiscible. However, even that immiscible solution, if that immiscible solution, if you heat, example, what is the effect of temperature now? It becomes soluble. That means partially miscible liquids can be made fully miscible by the application of heat. Now, this is our observation. We have to reason out our observation. Like any science theory, we have to reason out our observation using some yardstick, using some theory. So let us use some thermodynamics to understand why this happens. Okay, so this happens because for any process to be spontaneous, for any process to happen, what is the gold standard? That is the delta G, Gibbs free energy. If Gibbs free energy value is negative, that means if the free energy decreases during that process, then the process becomes spontaneous. So you take any spontaneous chemical reactions like exothermic reactions, delta G value is negative. The same thing can be applied for physical processes also. Like you can apply delta G for a chemical reaction. For a physical process also, delta G can be applied and seen whether that physical process is spontaneous or not. For example, what about our miscibility process? Mixing solvents and making solution. Is it a chemical process or a physical process? It is a physical process because there is no change in the molecular structures of the compounds during mixing. Therefore, this is only a physical process. Example, heating is a physical process, cooling is a physical process, boiling point is a physical quantity, freezing point is a physical quantity. So many a times in physical chemistry, we are looking into physical aspects, physical quantities rather than chemical properties. Anyways, now if the solvents, two solvents have to completely mix in each other, what is our condition? Delta G should be negative. Fine, good. Now let us see, for ethanol and water mixing, is delta G negative? Yes, it is negative for all temperatures and for all concentrations. But what about the delta G value for mixing of water and phenol? That has to be negative. If water and phenol will be completely soluble, that has to be negative. But always it is not negative. There are factors which control this sign of delta G. Different conditions will give different values for this delta G. What are those conditions? We will understand. What was the condition of miscibility? Small amount of phenol, large amount of water. It was miscible. Now let us see from thermodynamics point of view why there is miscibility when there is small amount of phenol and large amount of water. The answer lies in two other terms, delta H and delta S, thermodynamic parameters, which constitute this delta G. So if we look at the Gibbs free energy equation, delta G is equal to delta H minus T delta S. What is delta H? Enthalpy change. What is delta S? Entropy change. Now, for mixing, or when the solution is going to be formed for mixing, the delta S always increases. So the delta S becomes positive. Okay, there is slight increase in delta S during mixing. Fine. So delta S is positive. What is the value of delta H now? Delta H is also positive. Why? Because process is bit endothermic. Mixing of phenol and water is a bit endothermic. That means it absorbs energy from the surrounding. So delta H is positive. Now take the delta H, go to the equation and substitute the values of delta H. Delta H is a positive number. Delta S is also a positive number. Now, if I am doing the solubility test at lower temperature, keep T smaller, capital T, temperature value smaller. So after subtraction, what is the sign of the number which remains? Delta H is positive, right? So it is a positive number. Minus T delta S. Delta S is also positive. Temperature is low. So T delta S will be smaller in magnitude. So you are subtracting a smaller number from a bigger number, delta H. So what is the answer? Delta G will be a positive number. Therefore, the process becomes non-spontaneous. Mixing becomes non-spontaneous. Now, at smaller concentration of phenol, delta H value is small. Why? Because it is positive, of course, it is endothermic, but too much heat is not observed. Very small amount of phenol you have taken. Therefore, small amount of heat is absorbed. Delta H is a positive of low magnitude. Small positive number, delta H will be at smaller concentration. Delta S, as usual, will be always positive. So what happens? Since delta H is small, so it happens in that combination works out in such a way that delta H and T delta S. Delta H becomes smaller than T delta S. So subtract, you get a negative number. Delta G becomes negative and the process becomes spontaneous. But if you increase the quantity of phenol, that is when the immiscibility is seen, is it not? If you increase the quantity of phenol, what happens if you increase the quantity of phenol now? Delta H becomes more amount of heat is absorbed because phenol and water higher quantities are mixing with each other. More amount of heat is absorbed. So delta H increases. So now you are subtracting T delta H, which is smaller than delta H. Therefore, delta G becomes positive. The process becomes non-spontaneous. It becomes immiscible. The combination of phenol and water becomes immiscible. Is that all? There is one more factor which contributes for T delta S value, that is T, temperature. Till now, we have not discussed this temperature effect. What happens if you increase temperature? So the same solubility test I am doing at an higher temperature. So now T value becomes more. For example, at 25 degrees Celsius if you are doing, or at 70 degrees Celsius if you are doing. So T becomes more. Now T delta S becomes higher, bigger number. T delta S combination becomes bigger number. So even if delta H is more for large quantities of phenol and water, T delta S, because temperature has increased, it has gone up. So now you are subtracting a bigger number from smaller number. So what will be the value of delta G now? Delta G will be negative in sign. Therefore, the process becomes spontaneous. This is how we have to understand that at higher temperature, delta G becomes negative and phenol water becomes miscible with each other. So now this brings to our one more concept called critical solution temperature. So what is this critical solution temperature? It's simple. Critical solution temperature is the temperature at which the immiscible or partially miscible phenol water liquids become miscible with each other. How to find it out, the critical solution temperature? For that, we have to conduct a simple experiment. First of all, how to find out the miscibility and immiscibility? I told you, turbidity is the key point. If the solution is turbid after shaking, it is immiscible still. If the solution becomes clear, it is miscible. Now I have taken equal quantities of phenol and water. You have shake well and see whether it is miscible or immiscible. Immiscible, I told you, because when the small quantity of phenol and water, miscible. If I have taken equal quantities of phenol and water, it becomes immiscible. Turbidity is there. Go on eating this. Keep it in a water bath and heat. As the temperature increases, and when the temperature goes to a value which is equal to the critical solution temperature of that liquid mixture, turbidity disappears and clarity comes. Miscibility is seen. Okay, so when you are going to determine the critical solution temperature, all your observation is this: at what temperature turbidity disappears and clarity comes. That is what you have to determine. So now this is the CST apparatus. What does the CST apparatus consist of? CST, in fact, if there was no lockdown and there were regular classes, you should have done this experiment in your laboratory. This is an important experiment in third semester, where the students are required to find out the critical solution temperature of phenol water system. But you know, because of pandemic, because of these lockdowns, you are not able to do the experiment in laboratory. But hopefully, let us see, maybe the situation would improve in the coming days and you come back to the college, do this experiment. Nevertheless, still at least you can watch this experiment, somebody is doing this. Fine, this is the best thing what we can do now. How does the CST apparatus look like? CST apparatus is a boiling tube. What is a boiling tube? Boiling tube is a hard glass test tube. You know test tube, right? Test tubes are very small in size. But boiling tubes are bigger in size, higher volumes, and the walls are thicker. And this boiling tube has a cork on it. Cork has two holes. Through one hole you have a thermometer, through another hole you have stirrer. You have to take different volumes of phenol and water in this boiling tube. Put it in water bath. Find out the temperature of the water bath using a thermometer. Keep heating it and stirring this. At one point, you see turbidity disappears. record that temperature, and then remove the boiling tube from hot water and cool it in air. What happens when you cool it in air? As the temperature decreases, the clarity turns to turbidity at some temperature. Record that temperature also. So while heating, turbidity disappears. While cooling, turbidity reappears. Find out the temperature of disappearance of turbidity. Find out the temperature of reappearance of turbidity. One is for heating process, the other is for the cooling process. Find out the average of both the temperatures. The value will give you miscibility temperature. Okay, this is not critical solution temperature yet. It is miscibility temperature. And now you plot these miscibility temperature against different volumes of water phenol system. So if you do this, you find it, if you do this experiment properly and take your data, convert it into a graph, the graph should look like this. So what is this graph? This graph is nothing but the graph of miscibility temperatures of phenol water for different volumes of phenol water. So can you see on the x-axis, it is the phenol in water percentage by volume. What about on the y-axis? It is the average temperature of miscibility. You can see that as you as you increase the phenol volume in water, the lowest volume in this experiment is for about 8 ml of phenol in maybe 98 ml of water. Next point corresponding to some 15 ml of phenol in 85 ml of water. So go on increasing phenol's volume slowly, tube by tube. And then you find the miscibility temperature also goes on increasing. Okay. But what is expected? If you keep increasing the volume of phenol, the miscibility temperature should keep increasing in direct proportionality. But doesn't happen like that. Peculiar observation happens. At some composition of phenol water, there is a highest point of the graph, that is the maxima. This maximum temperature corresponds to some composition of phenol water. And after this composition, when you increase the phenol, the miscibility temperature starts decreasing. So the graph looks like a inverted parabola, is it not? Which has a maximum point value of temperature. This maximum value of temperature is called the critical solution temperature. Do you understand? So in fact, if you imagine this as a phase diagram, all the area enclosed within this curve represent two phases, water plus phenol immiscible. The area outside this curve represent a single phase, water plus phenol miscible. Therefore, construction of this curve for phenol water system is required to find out the critical solution temperature of phenol. So when you do this experiment, it turns out that from your experiment, the result is like this. The CST, critical solution temperature of phenol water system, is 66 degrees Celsius. What is the volume of phenol water corresponding to the CST? It is 43% phenol. That means a solution containing 43%, I should not say solution, a mixture containing 43% phenol in water is having the maximum miscibility temperature, and that maximum miscibility temperature is called critical solution temperature. Now, what is the significance of this critical solution temperature? It is simply this. See, 66 degrees Celsius is the critical solution temperature of phenol water system. Now, above 66 degrees Celsius, any composition of phenol and water is fully miscible. Above 66 degrees Celsius, any composition is fully miscible. Okay. Below 66 degrees Celsius, it depends on the composition. Few compositions are miscible, few compositions are immiscible. But above 66 degrees Celsius, all compositions are miscible. That is what the significance of critical solution temperature is. Okay, and now we have some more examples of partially miscible liquids. One example we have been discussing till now is phenol water system, and it's a very common example studied everywhere. But there are other examples also. Now, what the example here is triethylamine water system. Triethylamine is a liquid. Water is also a liquid. Now, for example, like you wanted to determine the CST of phenol water system. You are curious now to determine the CST of triethylamine water system. You will do the same procedure. You will repeat the same procedure. You take different compositions of triethylamine water, varying volumes, and then for each tube you go on to determine the miscibility temperature and plot it in the form of, and you record the data. Plot it in the form of a graph. You see a reverse behavior. What do you mean by that? Here, the critical solution temperature was the maximum point in your curve. But here, the critical solution temperature will be the minimum point in the curve. Okay. These phenol water system, critical solution temperature, maximum miscibility temperature, such CSTs are called upper critical solution temperature. Here, it is called lower critical solution temperature. So what is the value of lower critical solution temperature for this system? It is 18.5 degrees Celsius. So that means what? I mean, understanding this is a bit peculiar. Yeah? How? Why? Because at below 18.5 degrees Celsius, all compositions of triethylamine water are soluble. Above 18.5 degrees Celsius, only few compositions are soluble. That means we have a lowest point, that is the lower CST. This is called lower critical solution temperature. Okay, so what have we learned now? Critical solution temperature can be upper CST, upper critical solution temperature like phenol water system, or it can be lower CST like triethylamine water system. There is one more system which has both of it, upper critical solution temperature and lower critical solution temperature. What is this system? Nicotine water system. Nicotine is a liquid, water is a liquid. Now you go on recording miscibility temperature for different compositions of nicotine water. Keep increasing the composition of nicotine water. You find that you get a almost a loop. That means you get a oval shaped curve, and this oval shaped curve has a upper CST at 210 degrees Celsius and a lower CST at 61 degrees Celsius. That means all combinations of nicotine water is soluble above 210 degrees Celsius as well as below 61 degrees Celsius. Okay, so this is one interesting system which has both upper CST and lower CST. So it is not possible to theoretically predict CST using some equation. CST is a perfect experimental quantity which has to be determined only by doing the experiment. You can no way predict using some equations what would be the CST of this system. Not possible. Okay. Anyway, one small piece of information. The critical solution temperature, CST, is also called consolute temperature of the system. Critical solution temperature is also called consolute temperature of the system. This is one more term which was used in older versions of the books. But anyways, nowadays it is the critical solution temperature which is always used, universally used. It's not consolute temperature of the system. Okay. Now, why does this happen? In the sense, why does few systems have upper CST and few systems have lower CST? Usually, what is the effect of temperature on miscibility? Increasing the temperature should increase the miscibility, right? That is our common experience. But here, what is happening? Increase at 18.5 degrees Celsius, triethylamine and water are soluble in each other. But if you increase the temperature, they become insoluble, they become partially miscible, or the turbidity comes while you are doing the experiment. How to account for this observation? See, temperature usually increases solubility. Like maybe, for example, you would have done this, you would have seen this in your kitchens. Like when you want to do a sugar syrup to make jamuns, okay, ಪಾಕ ಸಕ್ಕರೆ ಪಾಕ ಮಾಡಬೇಕು ಅಂತ ಅನ್ಕೊಳ್ಳಿ. ಏನ್ ಮಾಡ್ತೀರಾ? ವಾಟರ್ಗೆ ಸಕ್ಕರೆ ಹಾಕ್ತೀರಾ, ಸ್ಮಾಲ್ ಅಮೌಂಟ್ ಆಫ್ ಶುಗರ್ ಹಾಕ್ದಾಗ ಚೆನ್ನಾಗಿ ಸಾಲ್ಯುಬಲ್ ಆಗುತ್ತೆ. ಬಟ್ ನಿಮ್ಗೆ ಜಾಮೂನು ಕಮ್ಮಿ ಸ್ವೀಟ್ ಇರಬಾರ್ದಲ್ಲ, ತುಂಬಾ ಜಾಸ್ತಿ ಸ್ವೀಟ್ ಇದೆ. ಸೊ ಯು ವಾಂಟ್ ಟು ಆಡ್ ಮೋರ್ ಶುಗರ್, ಮೋರ್ ಅಂಡ್ ಮೋರ್ ಶುಗರ್ ಟು ಇಟ್. As you add more sugar, the sugar doesn't get solubilized. So what do? You start heating it. In fact, you start boiling it, the water. In this boiling water, you keep adding sugar. Simply the water keeps taking sugar. But at some point, that means what? You can simply dissolve more sugar by heating water. Why did I give this example? To tell you that usually temperature has a positive effect on miscibility. It should increase the miscibility. But in this system, why is it decreasing the miscibility? Okay, the answer lies in its molecular interactions. See, triethylamine and water are bonded to each other through hydrogen bonding. When you heat, the hydrogen bonding becomes weaker. Why? The molecules are set into faster motions. And during these faster motions, the hydrogen bond becomes weaker and weaker. The molecules are going far from one another, right? So the hydrogen bonding becomes weaker and weaker. So at higher temperature, the hydrogen bonding is weakest. At lower temperature, hydrogen bonding is strong. Because of hydrogen bonding, triethylamine and water are mixing with each other. Now, due to increase in temperature, you are weakening the hydrogen bonding, which is responsible for solubility. So in a sense, you are disfavoring solubility. You are negating solubility. Therefore, at higher temperature, in some systems, like this is not the universal trend. In some systems like triethylamine and water, the solubility decreases as you increase the temperature. But how to account for this oval shaped curve? A system having both upper CST and lower CST. This is a bit difficult to reason out. Anyways, at your levels, the reason for such systems is not important. At least you should know the trend, how the miscibility varies with the increase in temperature and with the increase in the composition of the binary liquids. Okay, fine. So let me stop here. You please now send your names in the chat box.